question concerns two 100 amp services mounted side by side on a duplex. A grounding electrode conductor, or GEC, is run from service number 1 to the first ground rod. Another GEC is run from service number 2 to the second rod. The two services are then bonded with a jumper between them. All are terminated on the buses. The question is whether this violates 250.50. Also, the questioner asks what exactly is meant by 250.243. Yes, this scenario violates 250.50. Section 250.50 requires that the grounding electrode conductor from a service be connected to the grounding electrode at the service disconnecting means. In the described case, the grounding electrode conductor from service number 1 is connected to the grounding electrode at service number 1, but the grounding electrode conductor from service number 2 is connected to the grounding electrode at service number 2. This means that the grounding electrodes for the two services are not bonded together as they should be, which violates 250.243. Now, let's address what 250.243 means. Section 250.243 requires that grounding electrodes for a building or structure be interconnected to each other. This means that all of the grounding electrodes for a building or structure must be connected together with a conductor, typically a bare copper wire. This ensures that all of the grounding electrodes are at the same potential, which helps protect against electrical shock and fire. In the situation described, the grounding electrodes for the two services are not interconnected before the bonding jumper, which violates 250.243. To correct this violation, a jumper must be installed between the two services to bond the grounding electrodes together, but the grounding electrode conductors need to be connected together to create the interconnected grounding electrode system first. Let's delve deeper into the requirements of 250.50 and 250.243. The purpose of these code sections is to create a low impedance path for fault current to return to the source. This low impedance path allows overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and clear the fault, minimizing the risk of electrical shock or fire. When multiple services are installed in a building, it is essential to ensure that all grounding electrodes are properly interconnected. This interconnection creates a common grounding system that provides a consistent and reliable path for fault current. By bonding the grounding electrodes together, you equalize the potential between them, preventing voltage differences that could lead to dangerous touch potentials. Now let's consider the practical implications of violating these code sections. If the grounding electrodes for the two services are not properly interconnected, a fault on one service could result in a voltage difference between the grounding electrodes. This voltage difference could create a shock hazard if someone were to come into contact with grounded metal parts connected to different services. Furthermore, the lack of a proper grounding system could impede the operation of overcurrent protection devices, increasing the risk of electrical fire. To correct the violation, you must install a bonding jumper between the two services to interconnect the grounding electrodes. The size of the bonding jumper must be based on the size of the largest ungrounded conductor of the service, as specified in Table 250.66. The bonding jumper should be installed in a manner that provides a low impedance path for fault current. This means that the jumper should be as short and straight as possible, and it should be securely connected to the grounding electrodes. In addition to the bonding jumper, it is also important to ensure that all other grounding connections are properly made. This includes the connection of the grounding electrode conductor to the grounding electrode, as well as the connection of the equipment grounding conductors to the grounding bus. All grounding connections must be clean, tight, and corrosion resistant. Let's discuss the specific requirements for grounding electrode conductors. The grounding electrode conductor connects the service equipment to the grounding electrode. The size of the grounding electrode conductor is determined by Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor must be continuous and without splices or joints unless made by reversible compression type connectors listed for the purpose or by the exothermic welding process. The grounding electrode conductor must be securely fastened to the surface on which it is carried. Now, let's consider the different types of grounding electrodes that are permitted by the NEC. The most common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Ground rods must be at least 8 feet in length and must be driven into the ground at least 8 feet apart. Ground plates must have a surface area of at least 2 square feet and must be buried at least 30 inches below the surface of the earth. Underground metallic water pipes must be in direct contact with the earth for at least 10 feet. When multiple grounding electrodes are used, they must be bonded together to form a grounding electrode system. The bonding jumper must be sized according to Table 250.66 and must be installed in a manner that provides a low impedance path for fault current. In summary, it is essential to understand and comply with the requirements of 250.50 and 250.24 to ensure a safe and reliable electrical system. Failure to properly interconnect grounding electrodes can create a shock hazard and increase the risk of electrical fire. By following the code requirements and installing a proper grounding system, you can protect people and property from the dangers of electricity. Now, let's talk about some common misconceptions regarding grounding. One common misconception is that grounding is only necessary for safety. While grounding is certainly important for safety, it also plays a vital role in the proper functioning of electrical equipment. A properly grounded system provides a stable reference point for voltage, which helps to prevent voltage fluctuations and ensure that equipment operates correctly. Another common misconception is that any connection to earth is sufficient for grounding. This is not true. A proper grounding system must provide a low impedance path for fault current to return to the source. A haphazard connection to earth may not provide a sufficient path for fault current, which could compromise the safety of the electrical system. It is also important to note that grounding requirements can vary depending on the type of electrical system. For example, the grounding requirements for a separately derived system, such as a generator or transformer, are different from the grounding requirements for a service. It is essential to consult the NEC and other applicable standards to ensure that the grounding system is properly designed and installed. Let's discuss some best practices for grounding. Firstly, always consult the NEC and other applicable standards before designing or installing a grounding system. Secondly, use only listed and labeled grounding equipment. Thirdly, ensure that all grounding connections are clean, tight, and corrosion resistant. Fourthly, use a bunting jumper to interconnect all grounding electrodes. Fifthly, protect grounding electrode conductors from physical damage. Sixthly, inspect grounding systems regularly and maintain them in good condition. Seventhly, test grounding systems periodically to ensure that they are functioning properly. Now let's talk about the importance of proper documentation. It is essential to document the grounding system to ensure that it can be properly maintained and inspected. The documentation should include a diagram of the grounding system showing the location of all grounding electrodes, grounding electrode conductors, and bonding jumpers. The documentation should also include the size and type of all grounding conductors and connectors. In addition, the documentation should include the results of any grounding tests that have been performed. The documentation should be kept in a safe and accessible location. In conclusion, grounding is a critical aspect of electrical safety and equipment performance. By understanding the requirements of the NEC and following best practices, you can ensure that your electrical system is properly grounded and protected. Remember to always consult with a qualified electrician when designing or installing a grounding system. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Let's consider some additional scenarios and applications related to grounding. Firstly, let's discuss grounding in agricultural buildings. Agricultural buildings, such as barns and poultry houses, often have unique grounding requirements due to the presence of livestock and the potential for corrosive environments. The NEC provides specific requirements for grounding in agricultural buildings in Article 547. These requirements include the use of equipotential planes and the bonding of metal equipment to minimize the risk of stray voltage. Stray voltage can be harmful to livestock, and it can also create a shock hazard for people. Secondly, let's discuss grounding in healthcare facilities. Healthcare facilities have particularly stringent grounding requirements due to the sensitive nature of medical equipment and the vulnerability of patients. The NEC provides specific requirements for grounding in healthcare facilities in Article 517. These requirements include the use of isolated power systems and the bonding of all metal equipment to minimize the risk of electrical shock. Isolated power systems are designed to prevent leakage current from flowing to ground, which can be particularly dangerous for patients who are connected to medical equipment. Thirdly, let's discuss grounding in industrial facilities. Industrial facilities often have complex electrical systems with a variety of equipment and machinery. The NEC provides specific requirements for grounding in industrial facilities in Article 670. These requirements include the use of grounding electrode systems that are designed to handle large fault currents. Industrial facilities also often have a high risk of electrical hazards, such as arc flash, which can be mitigated by proper grounding and bonding. Fourthly, let's discuss grounding in data centers. Data centers are critical facilities that require a high level of reliability and uptime. The NEC provides specific requirements for grounding in data centers in Article 645. These requirements include the use of redundant grounding systems and the bonding of all metal equipment to minimize the risk of electrical noise and interference. Electrical noise and interference can disrupt the operation of sensitive electronic equipment, which can lead to data loss and system downtime. Finally, let's discuss grounding in renewable energy systems. Renewable energy systems, such as solar photovoltaic systems and wind turbines, have unique grounding requirements due to the presence of direct current, or DC, voltage and the potential for lightning strikes. The NEC provides specific requirements for grounding in renewable energy systems in Article 690. These requirements include the use of grounding electrode systems that are designed to handle DC fault currents and to protect against lightning strikes. Lightning strikes can cause significant damage to renewable energy systems, and proper grounding is essential to minimize this risk. By understanding the specific grounding requirements for different types of electrical systems, you can ensure that your electrical system is properly grounded and protected. Remember to always consult the NEC and other applicable standards before designing or installing a grounding system. Also, do not forget to consult with a qualified electrician when designing or installing a grounding system. Electrical safety should always be a top priority. This discussion provides a thorough understanding of the importance of proper grounding and bonding, the requirements of the NEC, and best practices for ensuring a safe and reliable electrical system.